Okay, I think everybody should be here now. I welcome everybody to this webinar about graph analysis and layout for developers. My name is Benjamin Niedermann. I'm a software developer at yWorks, and I'm happy to welcome you to the 6th episode of this series of webinars about the art of graph visualization. In this series, I show you how to create not only beautiful, but also meaningful and useful graph visualizations. And with this, I mean that you can actually create or derive new information from your graph visualizations for your connected data. And in the first 5 episodes, I gave a very broad overview on giving a lot of examples how to create such graph visualizations, considering different aspects. So for example, the layout and analysis, but also the styling of these graph visualizations and the integrating interactions. While I gave a lot of examples how to do this and what kind of aspects to consider, I didn't show how to do this programmatically. In this episode and also in the next 2 episodes, I would like to catch up with this and show how to do this programmatically using yFiles, so the main product of yWorks. And this brings us already to the tools for this webinar. So first of all, we will use yFiles for HTML. In case that you use other platforms like Java or C#, this is no problem because the API is basically the same on all of these platforms. So you will easily understand what we are doing here. Apart from that, we will also use the playground for yFiles that you can also access on our website. And we will use this playground throughout the entire episode to create a graph visualization. And I directly would like to go to this playground. And so if you also go to this link, you can also go, you will also get this playground here. The idea is that you can use the entire power of yFiles in order also to evaluate this, but also to just create a prototype for your own ideas. So when you start the playground the first time, you get basically this screen here. And on the left-hand side, you have here this possibility to write your code. And on the other side, on the right-hand side, you have a canvas where the actual graph visualization is drawn on. So the idea is now that you can change here the code or the graph visualization programmatically, and then directly you can try out what the effects are. And here in this very small Hello World example, you already see 3 important concepts of yFiles, namely the graph, then also the layout algorithms that you can apply here, for example, the tree layout, and then also the graph component. So when using this playground, what you get is a graph that you basically can create or you can configure. Here in this case, we create a graph with 20 nodes. We just create a single node for this graph. This is a typical way how you can do this in yFiles. And then based on this root node, we attach further nodes to this root nodes and other nodes by introducing randomly new edges. And then we get a tree structure that we then lay out, for which we then create a layout. In this case, the tree layout. And we do this by calling the so-called graph component, which basically represents the canvas here on the left-hand side. So the idea is that the graph component already knows this graph object, and then by calling morph layout, we apply this layout algorithm, and then we get this visualization on the right-hand side. And this is a typical approach in order to create a graph visualization with our SDK. So, and going back to the slides, I want to use this playground for a running example that I have used also throughout the other episodes, which you can also, by the way, find on YouTube. These videos we also will link below this YouTube video. So about the running example, this example is about a music database called Discogs. This is basically a Wikipedia-like database on audio recordings and which is maintained by thousands of users. And it contains millions of entries about releases, but also about artists and labels. So if you go to the corresponding website, what you can do, you can explore this database by clicking through the entries. So for example, here about the Beatles, but you can also click then on the artists, and basically you get a lot of information. And the nice thing with Discogs is that they also offer you an open API that you can use to derive the data, for example, in a programmatic way. And our example is based on this music database. So what we have done is, or what we had is the idea to create a graph visualization that shows the collaborations between artists. And a very simple way to do this is to introduce for each artist a node, here a red node for each artist, and then also a blue node for the music group. And the idea is then that an artist is connected to a music group if the artist is a member of this music group. So, and this gives you basically a collaboration graph. Of course, you can further introduce some styling, so you could label these nodes and so on. But in this episode, I would like to focus on basically on the layout. Having a look at this layout, the problem is that we don't get too much information about the collaboration because the temporal component is still missing. And in the last 5 episodes, I also argued and showed that it would be beneficial to introduce another visualization or another graph layout in which we can also see the temporal component, so how the histories of the artists is. And here the idea is that each artist is represented as an entire path in the graph visualization. So for example, Paul McCartney is here represented as a blue path going through the graph visualization, connecting the single music groups he is member of. And doing this for all artists, we get an entire graph visualization. And when you follow this idea, what you get is basically this graph visualization that you can also find in our playground. So I just go there. And so it loads shortly. Here you can access the entire source code for creating this graph visualization. If you run this here, this is computed on your computer live. And what we now can do is we can interact with this graph visualization. So we can zoom in and learn about the history of artists. So for Paul McCartney, for example, we can see, okay, he became a member of the Quarrymen in 1958, then in 1962, a member of the Beatles, and so on. So we can easily derive new information from this graph visualization. And in today's webinar, I would like to discuss how to create such a layout. And I would like to do this really on a coding level. So I will present a lot of code today using TypeScript and yFiles HTML. And as I already said, I will focus on layout. This means that I have introduced some simplifications for this webinar. So for example, I've decided that we just represent the nodes by small squares. So in this case, the red squares correspond to the artists and the blue squares correspond to the music groups. Further, I refrained from also displaying the genres, for example. Maybe you have noticed in the playground that I just, or that we also have group nodes containing genre nodes. But for this episode, I just let them out. So the webinar will be structured as follows. In the first part, I will talk about the graph. So I will talk about how to load the graph, analyze the graph structure, but also how to modify the graph. And then in the second part, I will talk about how to configure a layout, then how to refine the layout considering single elements. And then I will also talk about how to assemble different layouts together so that you get a more complex layout style. So let's start with the first part, namely, let's talk about loading the graph. And as I've said, we've extracted the data from Discogs, so of course only a small piece of the data, extracting two JSON objects, namely the object artists and the object groups. So the object artist consists of several entries. Each entry corresponds to an artist. An artist has an ID, name, and also the groups the artist is member of, and then also the number of releases the artist has published. And for the groups, we have a similar structure. We have some ID, which corresponds also to IDs here on the left-hand side for the groups object. And then the group, of course, has also a name, a first release date and a last release date, and then also some information about the genres the music group published in releases, and then also the number of releases. So this is basically the entire data that we are given, and now the idea is to load this data and create a graph structure based on this. And to that end, we need to decide on how to create the graph structure. And the idea is that we start with a simple collaboration graph that I've showed you at the beginning, which has no temporal component. And then later on, we will use this graph structure to derive a further graph structure that also contains the temporal component. So basically, this means that we introduce for each artist one node and for each music group a node, and we connect an artist with a music group if the artist is a member of the music group. So how to do this in yFiles? This is quite easy. The first part is that we create a graph, in this case, a default graph, and this default graph implements the interface iGraph. And when you already have worked with yFiles, you've noticed that typically you only have an iGraph in your hand and that you work on this iGraph. This is typically only when you create the graph, the only place where you really need to mention that you want to use a default graph. Apart from that, we also load the data. So this is basically the two JSON objects. If you want to know how this is done in detail, you can just go to the link here and see how load data works. But basically, it's a JSON object. And now what we need to do is we somehow need to extract the information from this JSON object and create the graph based on this. What you could do is you could just do this very similar as in the Hello World example, where you go through all entries of the raw data and create the nodes by hand. So by hand means that you just call the create node method on the graph and also the create edge method. Here I would like to present another approach, namely using the so-called graph builder, which helps you to populate a graph from custom data. So what we do is we create a graph builder object here, which already gets the graph. And now what we need to do is to define node sources for this graph builder. The first node source are the artists. So what we do here is that we tell the graph builder that the node source for the artist is given in the raw data .artists entry. So basically the large entry that you also can, or the entire object that you also can see here. And then what we also need to do is to tell the graph builder what ID we should use. And we just take the entry for ID of each artist. So this is the first node source that we want to use, but the second are also the music groups. So we do the very same also for the music groups. So here in this case, we tell the graph builder, okay, it should use the groups as node source, and then also it should use the ID of the group as an ID for the graph nodes. And now, finally, we also need to load the edges. And this we can do with the also by defining an edge source. But to that end, what we do is we first pre-process the data, creating a further edge data object that we then can pass to the graph builder. The idea is basically that we go through all artists And for each artist we introduce, we go through all group nodes, and for each group node we introduce an entry that consists of two sub-entries, namely source and target. And the source is the artist ID and the target is the group ID. And this basically corresponds then, for example, for artist 1 here to this three edges. And by flattening the map, we get only one array containing all edges. And this is the edge data. And then what we do is we create the edge source for this, telling the graph builder that it should use the edge data. And as a source ID, we say, okay, it should use the source entry here. And as the target ID, it should use the target entry. And yeah, this is already everything that you need to do to just load the graph structure from the raw data. The only thing that you need now to do is to trigger the entire process by calling build graph. And yeah, this already gives you the corresponding graph structure. I just want to show you this in the playground. And what I've done here is I call here this method load graph, and it's an asynchronous method, so I await this, and then I tell the graph component, okay, it should use now this graph structure as a graph. And then I also apply a simple styling. You can have a look at this if you're interested. And then I also apply a layout, and if I run now here, I get this graph visualization corresponding to our data. So the graph builder gives you a lot of many more possibilities to load the data and also to configure the graph. So for example, what you can also do is you can already style the graph using the graph builder. So telling or defining styles for the single elements using the graph builder. If you are interested in more details about this, I would like to invite you to go to our D-Guide, so to our developers guide, where you can find a lot of information about how to load a graph, also using a graph builder. So if I go there, here you can get an entire overview about yFiles and the main concepts, and there's also a chapter entirely dedicated to how to load a graph. Apart from that, you can also go to our tutorials that you can find on our demos page. And there are also more complex examples how to load a graph. So for example, it also will show you how to load labels, for example, how to configure them. But you can also find information about loading group nodes and configuring the styles. So if you go to this link here, you get to the demos, and here in tutorials you get more information how to use the graph builder. So this was the first step. Now I would like to show how to analyze the graph, and here I would like to show a typical pattern how this is done in yFiles. And the typical pattern is that you are given a class that represents the analysis algorithm that you would like to apply. In our use case, the connected components algorithm. This basically determines all connected components of the given graph and then results them, and you can analyze these connected components or work with these connected components. And the typical pattern is that there's one method called run, and this expects the iGraph, and then you get some result object that has further information about the graph. In our use case, it's really simple. We have here just the algorithm object, and we run this. And then what I've done, I've written an own print method that prints the number of components, but also for each component, the number of nodes. And this here is then the result of this run. And this pattern is very typical for the analysis algorithm. So we can also go to another analysis algorithm called cycle, which finds directed and undirected cycles of the edges in the graph. You have further possibilities to configure this cycle algorithms. And again, you have here one method with which you can call it. So what I've done here is I just created an instance of the algorithm cycle and told the algorithm it should consider every edge as an undirected edge, which means that if we don't find any cycle in this graph, then we can be sure that it's a tree or a forest in case that it consists of multiple components. So in our use case, we already have seen this also in the visualization. It's obviously not a tree or a forest, so the answer is false. But it's an acyclic graph. So in this use case, or in this case, we just tell the algorithm it should consider the directions of the edges. When we run this, then we get the information it's an acyclic graph, and by the construction, this is obvious because only edges go from artists to music groups, so we can't have created any cycle in this graph. So going to this playground again, you can also try this out on your own. In this case, so we have here this load graph again, and then we have here these single methods that are called for analyzing, and then the rest is again the same. So we can go there and you find the very same source code here. So this is a very typical pattern how to apply the analysis algorithms. If you want to know more about what kind of algorithms are provided, I invite you to, of course, have a look at our documentation, but also at our demos, namely in particular at our graph analysis demo, where you can basically see what kind of analysis algorithms we have. So here in this case, we see that we have just run different analysis algorithms, and here we get the results. But you can also apply here some of these algorithms to highlight some nodes. Okay, for the connected components, it's not very interesting, but for the minimum spanning tree, the blue edges show the minimum spanning tree. So feel free to play around with this a little bit to find out what kind of algorithms we offer. And now I would like to go to the next step, namely modifying the graph. So sometimes it's important, or after loading the graph, you would like to modify the graph in order to change the structure a bit, or in order to emphasize certain structures. In our use case, we would like to emphasize the temporal structure, so in which order the artists became member of the corresponding groups. So the idea is now that, for example, for artist 1, we would like to represent these edges here as a path going through the music groups with respect to the order of the first releases of the music groups. Here I just made the assumption that the artist first became a member of music group 1, then of music group 2 and music group 3. So the next step will be about how to take this graph structure here and change it to a graph structure like this. And this is also quite easy to do. So for this, I've introduced this function restructure graph. It expects the graph as an input, and it will change the graph in place. So first of all, what we do is we go over all nodes and identify all nodes that are artists nodes. When you have a look at this picture here, you will notice that all artists only have outgoing edges and music groups have no outgoing edges. This means what we can do is we can just select all nodes that have an out degree that is greater 0. And this is also a typical way how you can select nodes in our graphs. You just go through the graphs and then you use some typical filter functions, and then you decide for each node whether it's inside of the desired result or not. In this case, we use the graph property, but you could also use business data that you have attached to your graph structure. So, for example, the names of the artists. That's maybe also important to mention. I think I haven't done this when I talked about loading the graph. The entire, or for each node, you have a field called tag, and the graph builder basically puts all business data, so basically the entry data, at this tag so that you can easily access this. Later on, you will also see an example for this. So when we have all the artists, what we can do, we can walk through the artists and then identify the outgoing edges. And what I do is that I just take the out edges of an artist and then I put it in an array. Because what I now want to do, I want to change the graph structure, and in that case, it's better to first put all edges that I maybe later on will also delete into an array so that I can be sure that the iteration does not change or in an underlying way. So, and what I now do is that I just go through these edges and basically attach them to each other, forming the paths. And so I basically reattach them. And to that end, I start with the artist as a node, and I say, okay, this is the last node that I've seen on of this path. And then I go through these out edges and I create an edge that has a source at the, or whose source is the last node, and the target is then the target node of the out edge. And here you can see now the tag that I just copy to the new edge. Namely, I want to have a tag that consists of an entry artist. And this is basically the original tag of the artist that we are given. And as I said, the graph builder automatically copies the information to this tag when loading the graph. And what I then do here is that I update the last node so it becomes the target node of the out edge, and then the original edge is removed because I have created a new edge. And as a result, I get here this structure where basically the incident edges of an artist are translated into a path. So going to the playground. Here you can see how the method of restructuring, or the call of restructure graph, I just pass the graph that we've just loaded, and running this on our entire data, we get another view on the graph. And now you can see that, for example, here, this path, which corresponds to Paul McCartney, is actually a path. So in the example before, this was only a star emanating from the node representing the artist. So this is how you can modify a graph. This is also a typical way how you can do this in yFiles. And now I would like to talk about more how to create the layout. But as a side note, maybe, okay, this is a very important note. If you do modifications on your graph object or on your graph, then you typically don't do this on the elements themselves. They are basically read-only objects, but you always use the way via the graph object. So for example, here we remove the out edge calling the graph, or we create the edges calling the graph. So this is a typical thing that or way to do in yFiles. If you want to learn more about the graph model and also how to modify the graph, I again want to refer you to our developer's guide, where you find entire chapters about how to modify this graph. So, So what I now want to talk about is about how to lay out or how to configure a layout for a graph. And this will be also done in 3 steps. So let's start with the configure layout part, and this is also, oops, one moment. So here the idea is that we decide for one layout style. In our use case, I would like to apply the hierarchic layout. But of course, you could also apply other layouts, for example, the organic layout, or tree layouts if you have a tree structure and so on. And the idea is that you create an object representing this algorithm. So in this case, the hierarchic layout. And what you then do is you just configure some basic properties. So for example, the distance between the layers of the hierarchic layout. So here the idea is that the nodes are placed on layers. And now you would like to change the distance between the layers. Or you could say, okay, I would like to change how the edges are routed. In this case, I just said, okay, I would like to use orthogonal routing or the distances between edges. There are many different properties that you can use. And when you have created this layout algorithm, then you can tell the graph component to run this layout on your graph. Using morph layout, which basically then creates also this nice animation. In our use case, or in our example, we just use 1 second for executing this animation. If you don't want to execute or have an animation and just want to apply the layout, you can also directly call this process by taking the graph object and calling apply layout on the graph object with a given layout. So this is also a typical way how to do this. You have a channel settings of the layout style, which is then about the placement of the nodes, sorting of the edges, typically also about the labeling, but also maybe about the orientation of the layout, especially for hierarchic layouts. Here in our case, we decided to have a top to bottom orientation, but maybe you would like to have one that goes from left to right. But there are also settings about quality and performance. So there are many different settings that you typically can configure. And all of them are global settings with respect to the layout that you get. So let's go to the playground and execute this. So here in this case, I have here this method run layout. If I go there, you can see that I also configure here the hierarchic layout. And when running this algorithm, I get here already this basic layout of our graph structure. So as I already said, the hierarchic layout is not the only possibility, but there are many other layout styles for which you can decide and which you can use to visualize your connected data. So if you're interested in finding out what kind of layout styles are there, you could have a look at our demos about the layout styles. I would like to go to the next step now about refining the layout. And what do I mean with refining? So far we have just configured it in a global way, setting some global properties. But sometimes you would like to define properties for single elements, so for single nodes, for example, or subset of nodes. And this can't be done directly on the algorithm object, but you need to use a slightly different technique for this. So what we do is we still have this layout algorithms object, and what we also need to create now is the layout data object. So each layout algorithm in yFiles has a corresponding layout data object, in this case the hierarchic layout data object. And with this you can introduce proper configurations that are only meant for single elements, so for single nodes, for example, or for single edges. So let's have a look at the hierarchic layout data. I just show here 3 properties of this layout data, but it has many more. So for example, one property is this edge layout descriptor. And it's basically an item mapping. This is very typically on layout data. And this item mapping maps each edge, so each edge, on an hierarchic edge layout descriptor. And an edge layout descriptor basically describes how the corresponding edge should be routed in our layout style. And in our case, I would like to use this edge layout descriptor for some of the edges, namely for the edges that are incident to the artist nodes. And here I would like to change, for example, the routing style and also the length of the first segment. So here we get the old layout, and this is then the change. So what I do is I consider the edges incident to the red nodes. And for these, I tell the algorithm that the first segment should have a certain length, and then also that it should use, again, just a polyline style. And how is this done? So if you look here at the layout data, then a very typical way how to use the layout data is via delegates. So here the idea is that you define a lambda function, which is called for each edge. And then you can decide whether you are interested in returning an object for this edge, for example, in this case, the hierarchic layout edge layout descriptor, or whether you just want to use the default layout descriptor by returning null. So in our use case, I just go through all edges, and for each edge, I have a look whether the source node is an artist node, so a red node. And if this is the case, then I return an edge layout descriptor that has a minimum first segment length of 40 pixels. And by default, such an edge layout descriptor also uses a polyline style and not an orthogonal style, which basically means that we now get here for these edges incident to the red nodes, this kind of routing. And this is a very typical pattern. So again, what is done when the layout data is evaluated, this lambda method is basically, or function is called for every edge of the graph. And then for every edge, we can decide what kind of configuration we would like to return. There are also other possibilities to configure the layout data. So for example, using mappers, sometimes you already know which subset should have a certain property. In our use case, I have a highlighted path consisting of edges. These are the orange edges. And what I would like to do is I would like to straighten them. And the hierarchic layout allows us this by defining a critical edge priority for each edge, and edges with a high critical edge priority are preferred to be straightened. In our case, I just do this for edges on the same path, which means that this path will be straightened and becomes a vertical line in our layout or in our graph visualization. So in this case, I again go through all edges of the highlighted path. And then I set the critical edge priorities for each edge to 1.0, so for example, and all other edges have by default a priority of 0, which then tells the hierarchic layout, okay, the orange edges should be aligned or straightened. So these are two typical ways how to define properties for single elements. Sometimes you also want to introduce constraints between elements. So you have pairs of elements, for example, and you would like to introduce constraints. So for example, between two nodes. In this use case, I would like to, or in this example, I would like to introduce a constraint that tells the algorithm that all artist nodes, so all red nodes, should be placed on the same layer. And what I can do is I can, again, use the layout data, and this layout data has the property layer constraints. And this is a sub layout data, of the hierarchic layout data, and this offers you the possibility to introduce constraints between two nodes. So for example, here I use the first node as a reference node, and I tell the algorithm that the ith node, so the artist with index I, should be placed in the same layer as the first artist. And doing this for all artists, I basically tell the algorithms that all nodes that represent artists should be placed in the same layer. And so, for example, the hierarchic layout offers different constraints configuring or adapting the layout. So, for example, you could also introduce constraints telling the algorithm something about the order of the nodes within the layer. So you could say, okay, this node should be placed to the right of this node instead. Also using this kind of technique. And this is not only done for the hierarchic layout, but the layout data is a concept that is used for all other layouts as well. So let's go to the playground here again. And I go here to the run layout. I am here in the call. What you can see is that I also go through the edges of the graph, and I just filter all edges, or I just take all edges whose artist is Paul McCartney, and then I also convert it to an array, and then I call this method here. And then here the layout data is configured as I've described before. So I can run this layout here again, and we get the graph visualization as shown before. So, and finally, I would like to talk about the sixth step. So sometimes you want to also assemble layouts, and what you can do is one way to do this. There are several ways how to combine layouts, but what you can do is you can use layout stages. So typically you decide for one core layout. So for example, for the hierarchic layout, or for the organic layout. But sometimes you would like to also adapt this by introducing pre-processing steps and post-processing steps. So for example, a post-processing step would be that you adapt the routing slightly, which I will also show in a minute. And yFiles offers the concept of layout stages, and here the idea is that a layout stage wraps a core layout, which basically means that when the layout is executed, first the pre-processing phase of the layout stage is executed, then the core layout itself, and then the post-processing. And depending on the layout stage that you use, maybe both is applied, pre-processing and post-processing, but sometimes only one of these steps is applied. So there are many of these layout stages doing small tasks on your layout. So for example, there's the parallel edge router that you can apply to also route edges between, or multiple edges between the same pair of nodes. Or there's, for example, the component layout, which basically takes the single connected components, layouts each of these components, and then assembles these components with each other. And there are many different other layout stages that you can use. In our use case, or in our example here, I would like to show the polyline layout stage, which basically shows the typical application of these stages. So again, you have here this hierarchic layout, and then you also have here this polyline stage. And this polyline layout stage expects a core layout. This is the hierarchic layout. As I said, the layout or the stage is basically wrapped around this layout, core layout algorithm. And then we can also configure this stage. We could also use a layout data again for these stages. And then we call the graph component using the stage. And what we also could do if we configure these layout data, so for example, for the polyline layout stage, we could combine them with the layout data of the core layout. Here at this point, I also would like to mention that layout stages can be core layouts again. So basically a stage also implements the interface of an iLayout algorithm, which basically means that you can do a nesting of these stages. So you can apply several stages and then the core layout by just defining again, for example, another stage that expects then or takes the polyline stage as core layout. In this case, I applied the polyline layout stage in order to introduce octilinear segments on these orthogonal segments. So basically, what we do is here we replace these small right angles with some segment, getting a by basically rounding up these corners. So going to the playground, we can also see the result. So going to the one layout, this is basically done here in this part where I just created the polyline stage, and when I apply the layout, I get this visualization in which we have introduced here these segments as an example. But there are many other stages that you could also apply to change your layout. So in this webinar, what you've seen is typical steps that you can apply to create graph visualizations in a programmatic way using yFiles HTML. So when you talk about the graph structure, it's often about loading, analyzing, and modifying it. And then the next step is typically configuring the layout. And there are typical steps like the layout data, which also gives you the possibility to configure the layout for single elements, but you can also assemble different layouts. So what you should take from this episode is typical patterns that you can use in yFiles to obtain your desired graph visualization. And with this, I already would like to wrap up with the main part of this webinar. The next webinar, which will take place in May, will be also about creating graph visualizations programmatically. And this time it will be about graph styling, so how to define styles for the nodes and for the edges, but also about animations. Yeah, and with this, I would like to go to the next part of this webinar, namely the question session. And now I will have a look at the chat and we'll see what kind of questions you have, and then I will answer them in 1 or 2 minutes. Okay, the first question is, can you let us know if we can use the sandbox to try things out on our own data? If yes, what are the limitations of the sandbox, and can you confirm that use data remains local? So yeah, first about the things that the data remains local. yFiles for HTML, for example, and the playground is written in or uses yFiles for HTML, runs completely on the client side. Basically, so when you execute the playground, it's completely run on your computer, and no data is transferred somewhere else. So it remains local on your computer. The next thing, can we use our own data? Yes. So in the playground has a lot of examples showing how to integrate also your own data. So what you can do as the most easiest way is just copy the JSON object into the code and interpret it as a TypeScript object, and then you can work on this directly. This is one way to do. I think there was also the third part. If yes, what are the limitations of the sandbox? So basically, you can try out most parts of yFiles with this, and can have a look at this how yFiles work with this. So it's basically contains or comprises the full power of yFiles. So next question. The next question, is it also possible to lay out parts of the graph with different algorithms? So I said that you can combine the algorithms, that you can combine layout algorithms, but I only showed how to run it on an entire graph. But what you can also do is, yes, you can also run them on different part of the algorithms. Herefore, you can also use layout stages. So for example, if you have a graph structure with group nodes, what you can do is you can apply the recursive group layout, which is also this layout stage, in order to tell the algorithm that certain components, certain groups should use certain layout algorithms. So for example, a chronological layout, and another group could use a hierarchical layout, or you just want to use another layout for the top level and for the content of the groups, different layout algorithms. What you also could do is you could use the built-in layouts for some of these major layouts. So for example, the organic layout has a substructure detection that basically detects certain substructures, so like stars, and then applies certain layout algorithms internally to get a better better layout for this. The next question is it possible to tell the algorithm on which side of the node the edges should end? Yes, that's also possible. So for this, we have the concept of port. So a port is basically an element in our graph that is the connection between the edge and the node. And what you can do is, for example, in the hierarchical layout, you can introduce port constraints or candidates with which you can tell the algorithms where a specific edge should end. So for example, you could say, okay, it should end on the top side of the node or on the left side, but you can even be more precise by defining specific offsets, for example. Yeah. About data formats, and the question what we support for formats for data. And this is a very trivial question, and the answer in general is that it does not depend very much on the format of your data. What you can do is you always can write your own data connector, which translates your data into a graph structure. And so when you have achieved this, so when you have this graph structure in your hand, then you can apply the yFiles algorithms without any dependence on your data format. But as you have seen, there's, so for example, direct support for JSON formats using the graph builder, but also for GraphML, which is a standard XML format for graphs. But as I said, it does not depend very much on the data format. It's more about writing a data connector, and then you can apply yFiles. Next question, is there a limited amount of nodes and edges to render with a good performance on yFiles? I'm running very large graphs and I would like to optimize the performance. What techniques are there available? With yFiles, you can basically render thousands of nodes, and then often it's more about the rendering. Of course, it also depends on the layout algorithms that you apply, but when you let's assume that you just want to render these graphs. What you can also do to speed this up is use WebGL. So yFiles also gives you the possibility to use WebGL to improve the performance of the rendering. Is it possible to load data from a connection to local to a local Neo4j database? And with yFiles, you can load data from a Neo4j database. Basically, we have also a demo on this, how to do this. Maybe we can also post this link in this Zoom chat. But we can also send you this link to this demo. But yes, this is possible. Okay, I think there are no questions. And with this, I would like to wrap up the entire webinar. I thank you for your attention and wish you a happy diagram.